In-process inspection has been widely used for many years in many different industries because of its proven benefits. Modern manufacturing, whether automated or manual, actively measures product quality throughout the process to understand process variation. Using methods like statistical process control, or SPC, the earlier flaws or defects are detected, the lower the cost to identify and correct the problem. All processes have inherent variation in feedstock materials, process parameters, machine operations and operators that affect final part quality. This variation can increase scrap, rework, and production costs. We can measure these effects by monitoring the process in real time. When a defect is noted, we can stop the process to take corrective actions. In machining, for example, we can perform an intermediate or in-process inspection of machine features using a touch probe in this example. From this information, we can calculate the precise amount of tool wear. If there is sufficient wear, we can perform a second machining step to compensate for the known tool wear as seen here. Laser powder bed forming, or L-PBF, has many process variables. Some are programmable, but others like powder particle size, spatter formation, laser plume effects, etc., are stochastic or random in nature. They cannot be effectively pre-programmed. To better understand the quality of the as-formed layer, some systems use melt pool monitoring. Here, process parameters like the melt temperature are recorded during the process. This is useful as the quality of the as-formed melt layer depends, in part, on process parameters. However, it's important to recognize that this is an indirect measure of the as-formed metal layer quality, which also is affected by other factors. Flightware has developed an in-process inspection method for L-PBF that directly measures the as-formed metal after every layer is produced. We measure the surface height or profile of the melt layer using a commercial off-the-shelf laser profilometer. This provides a very dense and very precise 3D point cloud of the surface. We generate about 4 million points per square inch, and height measurements are repeatable to less than half a micron. In earlier work, the profilometer was mounted to the powder recoater arm. The line sensor generates an area scan due to the motion of the recoater arm, which occurs at the same time and in front of powder coating. By scanning in parallel with powder coating, no additional cycle time is added to AM fabrication. Surface profile data is fed into an algorithm called the Layer Topographic Map, or LTM. Layer data is subdivided into smaller windows, each representing a small region of the layer. Profile data in each region or window is then characterized by two parameters, and these parameters are plotted as an XY data point for all regions in the layer. Good or nominal quality points or layer regions lie in a roughly elliptical area of the plot. We then define a boundary for our baseline to differentiate between nominal quality and defects or flaws. Data is processed for every newly created layer. If a point lies within the nominal boundary, the point is marked black. In most cases, the majority of the melt layer consists of nominal regions, such as shown here. In some cases, however, point or regions of the layer lie outside the nominal boundary and are identified as flaws. These points are marked in red, as shown here, where almost every part of this layer shows as a flaw. During the build, an LTM map is created after every layer is formed. Flaws are detected as soon as they are created. We see here an animation of the part build in the center of the screen. After every layer, an LTM map of that layer is created, shown in the screen inset in the upper left. The predominantly black dots signify good or nominal quality layers. For one layer, however, we see predominantly red dots or flaws. In this case, we had intentionally created or seeded flaws at that layer so we could later verify and correlate those flaws via CT scan. After the flaw layer, we continue to build up the part by adding and inspecting additional layers. Subsequent CT scan quantified the magnitude and location of porosity in the final part. In this case, porosity was created by using low power settings known to create lack of fusion flaws. Flaws were created in known locations with physical fiducial marks in the part to allow accurate registration of the CT data. This data was then processed to isolate and measure porosity in the as-made part. CT results were correlated with LTM results to determine LTM algorithm performance. We determined the probability of flaw detection, true positives, and the false alarm rate, false positives. In total, more than 1,800 layers were produced in multiple test parts, where 55 layers contained seeded flaws. The LTM algorithm correctly found or detected 54 of these 55 flaws. It also found or detected 18 flaws improperly within the 1,758 nominal quality layers. The math indicates a 98.2% probability of detection. Put differently, the algorithm missed 1.8% of the flaws present. The algorithm also produced about 1% false positives. These early results were very encouraging. Flightware is currently under a follow-on contract to the Defense Logistics Agency to extend this work. This includes extending the profilometry system to cover the entire powder bed and further development of LTM in-process inspection algorithms. To summarize, an in-process inspection method was developed based on direct measurement of the as-formed metal layer. Initial results show the algorithm performs well and reliably detects certain types of L-PBF flaws. This work is continuing under DoD funding.